Okay, let's get started. Today's material will be the last material that will be covered on the midterm exam. Monday we'll have a lecture, but that material will not be on the midterm. I also realized as I was walking over that I forgot to post these slides on BSpace. I'll do that as soon as the class is over, along with the homework for this week. Oh, there will be a homework that's posted. Will be posted today. Next Friday we're not going to have a class. If you leave early for vacation, it's okay if you turn it in the Monday when you get back from vacation, so don't have to turn it in on Friday. We're talking now about phase transformations that result from deviations from global equilibrium. There are two basic mechanisms. This is a thing to get straight because it is important. There are two ways in which a transformation from hypothetically a high temperature alpha phase to a low temperature beta phase can happen. One way is that new particles of the beta can nucleate into the alpha. If they're big enough, they become thermodynamically stable and they'll spontaneously grow until they consume this parent phase. The other thing that can happen is that the alpha can become so far below equilibrium that it actually becomes unstable and spontaneously transforms. In this graph, I show it spontaneously transforming to beta. That may happen, or it may transform to something else. But if it becomes unstable, it can no longer exist and it must transform. We talked last time about the nucleation and growth transformation. The important thing to remember about nucleation and growth transformations is that their kinetics are given by a C-curve of the sort like it appears here. There are two interesting features of this C-curve. One is that it does have a nose. There is, well, three things really. First of all, it is always necessary to have some undercooling in order for a transformation to happen. Transformations do not happen at the melting point or the phase transformation point. They happen after some further undercooling. The second important feature is that there is a nose to this curve. That has the consequence that it is possible, if you can cool the system quickly enough, to suppress the transformation by cooling past this nose. Now, in some transformations, even when you get down to low temperature, the transformation curve is still close enough on the time axis that the transformation will happen. But in many cases, when I get down here to low temperature, this curve is so far out that the transformation will just never happen at all in practical terms, and I've successfully suppressed it. This allows us, for example, to do heat treatments in which we suppress the transformation by cooling and then reheat so that we can control the temperature at which that transformation occurs. An important reason for doing that, and that's the third interesting feature of this nucleation and growth behavior, is that the mechanism of the transformation, the pattern of the transformation, changes depending on where we are on this curve. In most materials, when we're up at the top of the curve here, we're in a situation where the kinetics of the transformation is dominated by the difficulty of nucleation. That means that the transformation will occur preferentially at those sites where nucleation is easiest. And these are the heterogeneous sites, such as grain boundaries in a polygranular material or dirt particles in a glass of beer or whatever. And so you can control where the transformation happens up in this region by, for example, artificially introducing a group of nucleation sites. Done often in welding, for example, to get grain refinement in the welding. You do what's called salting the weld. You mix tiny oxide particles into the weldment. The solid nucleates on those oxide particles, and as a consequence, you can get a very fine grain weld. There are many uses of that. Even more common is the use of the lower end of this region, where the behavior is dominated by growth. Nucleation is easy, growth is a problem. And as a consequence down here, in, for example, a polygranular body, you'll get a shower of nuclei more or less everywhere through the volume. So if I get my transformation, if it's a precipitation reaction, for example, and I get it to happen down here, then I can get precipitates more or less uniformly dispersed through the bulk. That's what I must have if I'm going to use an array of precipitates, for example, to harden the material. So this kind of this behavior is also important. Well, as a quick aside, I said this yesterday. What I've said refers to transformations that occur on cooling. When the transformation occurs on heating, no such nose, no such C-curve appears. And the reason is that as I go up in temperature, both nucleation and growth become easier. So the transformation gets easier and easier and easier as I go up in temperature, and therefore cannot be suppressed. You see an example of that in the lab you're doing now, where you're studying the recrystallization reaction in copper. The higher the temperature, the faster that recrystallization occurs. And of course, the higher the temperature, the more rapidly growth occurs. So where you have worked the material and then subjected to high temperature, you see very large grains. They nucleated quickly, and they had time to grow, and therefore grew to large size. You can use that kind of process in recrystallization. We do use it. I'll get back to this later. It's kind of the standard method of controlling the strength of, for example, typical steels and used for automobile applications and things like that. Instabilities. If you take a system, cool it sufficiently far below the transformation temperature, it is in many cases, it will become unstable and will transform spontaneously. The important thing to remember, two important things to remember about these instabilities. They cannot be suppressed. They will begin when the instability point is reached. So we don't have a C-curve for spontaneous transformation. It's simply a line, a temperature at which it commences if we can get to that temperature without nucleating. The second thing to remember is that when we have an instability for profound thermodynamic reasons, we always go unstable with respect to one variable, never to multiple variables. So if we have a transformation in which we change hypothetically the structure, the composition, and the state of order, for example, precipitating an ordered precipitate out of a solid solution, if we drive that by an instability, we will change only one of those, the composition, or the structure, or the state of order, never all three. A classic example of a structural transformation is the formation of a glass. We talked about that earlier. We cool quickly enough from the liquid to suppress crystallization, we get a glass. The glass has the composition and the state of order that the liquid had. The only thing that we changed is the structure, in this case the inhibition of the motion of those individual atoms. The most important of the instability transformations historically in current technology is the Martin-Sittig transformation in steel. There are similar transformations in many materials, where a structural transformation that would ordinarily occur on low temperature is suppressed until the high temperature phase becomes unstable with respect to a spontaneous change in structure. In steel, that's the Martin-Sittig transformation. It's characterized by transformation over a range of temperatures, because when the spontaneous transformation from FCC to BCC happens, it is a violent disturbance of the lattice, producing, for example, lens-shaped figures like this. It distorts the surrounding lattice and therefore makes it more difficult for the transformation to continue. For that reason, if we want to keep a Martin-Sittig transformation going, we've got to keep cooling, because we have to provide more and more and more driving force to overcome not only the thermodynamics of the transformation, but also the strain energy that's involved by the previous particles. So you end up with very messy microstructures in Martin-Sittig steel, and materials that are very, very strong and very brittle. Of course, the only thing you're changing in this case is the crystal structure. That's the only thing with respect to which you are unstable. So if the steel contains carbon, as they normally do, a supersaturation of carbon is trapped inside this lattice. If you want to get back to some equilibrium carbon, you have to temper the steel and let the carbon out by precipitation. Instability is one variable only. There are also instabilities that involve chemical composition. These are what's called spinodal decomposition. I mentioned earlier when we talked about the phase diagram of a simple solid solution, is that such a phase diagram is deceptive. All materials, because there is a third law of thermodynamics, the entropy must go to zero as temperature goes to zero. All materials must either segregate or order at very low temperature so we get to a finely ordered state. a common situation, which sometimes appears in the phase diagram and sometimes does not, is that the solution will have what's called a miscibility gap. As we go down in temperature, the alpha solid solution, hypothetically let's call it FCC, will split into two solutions that have the same crystal structure with different composition. That creates a two-phase region, alpha prime plus alpha double prime, that describe a miscibility gap that looks something like this. If you take this solution and you quench it into this miscibility gap, if you get well within the miscibility gap, the composition will become unstable. At constant crystal structure, you will begin to develop a separation by composition. The way that ordinarily happens is the development of sinusoidal waves, because we can show that there are certain critical wavelengths of a composition wave that will grow more rapidly than others. So what you can actually see happen in this case is the development of surprisingly sometimes sinusoidal waves in which the concentration varies with distance. Over time, the amplitude of these waves grow until eventually you get the equilibrium separation. That's a spinodal instability, an instability in the compositional variable only. The structure stays the same, the state of order stays the same, the only thing I change is the composition. Finally, there can be changes in the state of order. They can happen as first order transformations or, well, let me say, there can be transformations in the state of order. I haven't shown an example here, but you can get ordering instabilities as well, in which order spontaneously develops an isolated solution. You can also have, and you do have in a number of important physical systems, transformations that occur through a cascade of instabilities, where, for example, we'll have a spinodal decomposition, and after the composition difference gets great enough, one of these compositions will spontaneously order. So we wind up with a very intricate mixture of an ordered phase and a disordered phase. The first graduate out of my research group went to Bell Labs from here and invented something called Chromendor, which was a very, very good magnet material that has been used in every telephone headset of a certain generic type for the last 40 years. What he did in that, he wanted to create a material that had very small islands of ferromagnetic material embedded in a non-magnetic matrix. So he arranged a situation in which he got a spinodal decomposition. With one of these, once the composition reached a certain value, one of the two ends of this phase became ferromagnetic. So he wound up with ferromagnetic, paramagnetic, ferromagnetic, paramagnetic, and made a hell of a good magnet that's still used today for many applications. So lots of applications of this kind of procedure, and often they do involve accomplishing a transformation through a cascade of instabilities to get the right kind of distribution of your final product. Very difficult to think of another way to make a material that has regularly spaced discrete islands of ferromagnetic phase, but this does it automatically. I also told you that there are transformations that are mutations in which one phase simply becomes another. Well, the reason one phase becomes another is it becomes unstable with respect to that change. But in a mutation, we have the situation where the phase transformation point and the instability point coincide. So the phase transformation, we don't need nucleation, we don't need martensite. The phase transformation occurs by an instability, and one phase simply becomes the other. Classic examples are the ferromagnetic transformation. Well, in this case, I show order. This would be, for example, the beta brass, copper 50-50 copper zinc. High temperature, I have a solid solution. I drop below the transition temperature, which is known as the Curie point, out of Madame Curie's definition for ferromagnetic transformations. And at this point, we begin to see order. Initially, only a tiny bit of order. When we're right here, there's just a slight statistical tendency for copper to be in the center and zinc to the outside. As we go down in temperature, the order becomes more and more perfect, measured by this parameter eta, until at low temperature, we have perfect order if it's 50-50. All of the corner atoms are copper, all the center atoms are zinc, or vice versa. That's a mutation. It's an example of an instability, but it's just a case where the instability point and the phase transformation temperature coincide. Okay. Well, I talked about nucleation, and I said transformations were one set of transformations were nucleation and growth. Now it's time to go back to that and talk about the growth issue. Once we nucleate a particle, how does it grow, and how does that affect the microstructure that we eventually have? There are really two mechanisms of growth, or modes of growth that we can distinguish. In many cases, the growth is what we call interface control. That means the rate-limiting step. As an example to visualize, imagine a solid growing into either a liquid or a vapor. It's a prototype example. Under interface control, the problem that you have is incorporating the molecule from the liquid or vapor into the solid. For example, in a vapor, you really have to have two steps to get the atom into the solid. The atom has to get on the surface, absorb onto the surface, and then it has to find a place to sit so that it incorporates into the solid. So that may be the controlling step. If we can get more atoms to the surface, if we can get atoms to the surface more easily and more quickly than we can incorporate them, that's what we call interface control. The rate-limiting step is incorporating the atom into the surface. We affect it by the structure of the surface, and that leads to, we can actually use that in unstable growth leading to things like whiskers and nanowires. I'll talk about that in a minute. The second mechanism is growth control. In growth control, our problem is not incorporating anything into the interface, but getting it there. If I'm growing a solute-rich precipitate out of a solution, I've got to diffuse the solute to the surface of the precipitate before it can possibly be incorporated. So I have growth control. My growth is going to be controlled by the rate in which I can get the solute there. In crystal growth, normal crystal growth, I have the opposite problem. The transformation liberates heat, and I can only grow as fast as I can dump that heat into the environment. So there, the growth control is how fast I can dump the heat from the growing interface. Let's look at some examples. In interface control, we have atoms coming to the surface. We need to incorporate them into the surface. If the surface is crystalline like this, the normal incorporation will be at steps, something like this. The atom will fit into a corner or step, and in that way the crystal will grow. Well, that may or may not present a problem. And here's just a simple Arrhenius expression to give you the rate of growth under those conditions, in which we have both a driving force, which is the drop in free energy when the atom is incorporated, and also a barrier, which is the barrier to incorporation. There's always some barrier to the motion of atoms. Since atoms incorporate at preferential sites, that may or may not be a problem. If we take crystalline solids that have reasonably isotropic surface energies, like most metals, and we take them up to moderate temperature, then the surface is in fact irregular and diffuse. An atom comes to the surface, there are all kinds of places for it to incorporate, because the surface is kind of rough and irregular, and there are many, many ledges that the atom can fit onto and incorporate into the solid. If, on the other hand, the solid we're talking about has a very anisotropic surface energy, or if we're talking about low temperature where the surface isn't enough entropy to make the surface diffuse, then our surfaces tend to be very regular. And then the atoms can only incorporate at the edges or corners of rather well-developed close-packed planes. And this is true of the growth of many compound crystals, of many complex crystals where we're crystallizing organics or things like that. We have this situation. When we have that situation, we have a rather serious kinetic problem. Because imagine that we have a surface which looks like it's shown here on the right initially. For some reason, we have roughnesses here. Here are the edges of various steps, and atoms are incorporated there. Well, that will cause the steps to progress. But before too long, the steps reach the end of the crystal and run out of their progression. And the crystal develops low index and distal surfaces, and in theory can't grow anymore. And in fact, one of the great barriers as people developed theories of crystal growth and simultaneously theories of dislocations was how is it that crystals actually grow? Because if you get rid of the steps, then the only way you can continue growth is by nucleating new steps, by a two-dimensional nucleation process. And you can easily calculate that this is difficult to do. So back in the early 50s, most of this was being done, when people were trying to get a good handle on how crystals grew out of the vapor, out of the liquid, they were having real trouble figuring out how you got past this nucleation barrier. Turns out there are two ways to get past it. And the first that was developed and was simultaneously a major step forward in the visualization of dislocations in solids was people realized that if you had a crystal like this, flat surface, and if that surface was penetrated by a screw dislocation, as you remember in the screw dislocation, you start out on a plane, go around the dislocation, come out on the next plane, go around, come out on the next plane. The same is true in reverse. If I have a screw dislocation right here and just a natural interface around it, that interface will be like a spiral pyramid, spiraling around the dislocation. So if I have a screw dislocation penetrating through the surface, I can grow the crystal by absorbing atoms at the edges of steps in a process that never slows down and never stops. As the edge advances, the spiral here just winds around the dislocation, generating new step after new step after new step, more or less forever. Well, people thought maybe they could observe that. And in fact, the very first really clear observation of a dislocation was an observation of this process in action. It was the tobacco mosaic virus. I don't know what the hell it is, except it's rather big, and it does crystallize. And since the mosaic virus crystallizes and is rather big, the steps are huge. And as a consequence, they were able to look at these very carefully. And they actually observed screw dislocations and the spirals and the steps and the pyramids and the crystallization of this tobacco mosaic virus crystal by screw dislocation. And it was the first visual demonstration that dislocations are real. It's a method of crystal growth. Well, you can, whiskers. You can start things growing. Sometimes happens to be a real problem in some systems, maybe a benefit in others. But if you get big particularly out of the vapor under the right conditions, and also out of liquids, you can get a single screw dislocation growing fairly rapidly. But if it becomes horizontally limited, if this dimension is not too big, it will produce something that looks like an Egyptian obelisk. Very, very tall, very, very thin, with kind of a pointed top. This has only one dislocation in it. If you can subsequently persuade that dislocation to climb out by heating it or something of the sort, this is a way of creating an absolutely perfect crystal. Not too big, but perfect. And many years ago, people discovered this and used it to do the first studies on crystals that you could assume, except for a few vacancies, were really, really perfect. No dislocations, perfect crystal. And these whiskers, this is still used as a method of generating some kinds of fibers. There's a second way. Well, let me give you kind of a funny example that we encountered some years ago, many years ago actually, in work on lead tin solder. In lead tin solder, you have a lead tin here, copper here. The copper interacts with tin to produce an intermetallic copper 6-tin-5. And we saw the most bizarre thing. They tend to grow as columns, like whiskers from the interface. And we would find out here in the solder sometimes some of these columns, and in cross-section they look like this. They look like kind of, well, this is a slightly distorted hexagon, but they would have hollow cores. They would have the eutectic material inside. And this seemed very puzzling for a while until we realized it had a very simple explanation. These things are growing by a screw dislocation mechanism. So they have a screw dislocation right at the middle. Once these whiskers break off of the surface and get out here in the bulk, they are no longer preferred because there isn't rich enough copper, and so they tend to dissolve. Well, when they dissolve, the first thing to dissolve is the highest energy material. And the highest energy in this hexagonal column is the screw dislocation core right down there. So they tend to dissolve in the core. We in fact found some that were partially dissolved where you can see where it terminated. So you get bizarre things like this from whisker growth. The one that has become very prominent in recent years, and Pei-Don Yang over here in the chemistry department has been a big pusher of this kind of thing. Now we really like to grow whiskers as nanotubes, thin fibers, and so on to various nano devices. One way to do that is, this is a paper, classic paper about Pei-Don Yang, a student back in 2001, growing germanium crystals of almost perfect crystals. The way you can do that is suppose you find a phase diagram as a simple eutectic, something like this, where you can get a situation where you have a liquid phase and a solid phase and a eutectic. Notice the eutectic temperature is way down here, very low. So suppose I seed with germanium, and I can coat the germanium with a little bit of the eutectic phase, in this case gold germanium. Now I bring in a vapor that's germanium rich. So the germanium starts getting incorporated, dissolves more easily in the liquid eutectic than in the solid phase. So the germanium keeps coming into this eutectic. Well, as soon as it comes into the eutectic, out plates germanium. And since germanium and gold are virtually insoluble in the solid state, the thing that comes out is essentially pure germanium. So I have this little ball of liquid on top, and I can just grow it by this process, and that's a very useful and very popular way to generate these long nanofibers that you see being out there. I had to laugh when I first saw this, and I thought Pei-Don gave back about that point, because this is 2001. And I remember a lot of techniques in processing. Someone discovers them in basic research, and they're not just particularly useful at that point, so they come out, they go into literature, and then they disappear. I heard a talk on this very process in 1964, which was almost 40 years before it kind of hit as the hot new thing. And I know it was 1964 because it was a talk given by a fellow at Bell Labs, and he had used this process. It wasn't this system, I forgot which system it was, but exactly this process. He just put on these eutectic dots on the surface, and out would sprout these pillars of whatever he wanted to grow. And this was 64 was the year of the Goldwater-Johnson presidential campaign, and he had to be a big Goldwater fan. So what he had done with this was to spell out AuH2O in nanofibers on the surface. And that's a visual image you don't forget real quick. So I know he did it, and I know he did it in 1964. It didn't turn out